Welcome to the second talk of the morning session today. And we are very happy to have with us Nguyen from Ohio State University. And Hoi is going to talk about random matrices, algebraic statistics, and universality.
Thank you for the introduction, and thank you very much for the invitation. It's a great pleasure to be here. So I'm going to speak about something quite unusual on random matrices, but on a totally different aspect of it, namely the algebraic statistics. Some of those are very elementary. Right, so the matrix model that we have here is we call IAD matrices. So P is a prime number, and for the most part of the task, we'll be fixing P. And we have a matrix Q, square matrix of size n by n, and the entries are uniform over FP. Okay. We can do it over other fields as well, but we are working with prime field for convenience. Right. So the dimension is sent to be infinity, and P is fixed again. But although there's some part of the method also works for P growing together with n. So we are interested in the rank statistics of matrices of this matrix Q, or the co-rank statistics. Right? Rank n minus d means that the co-rank is d, and for each fixed d, we're trying to calculate what is this probability for each fixed d. And of course, some cases we're also interested in the other version of matrices, namely rectangular matrices of size n by n plus u. Let's say we fix u, u is 0, 1, 2, 3, and so on. We're interested. So let's just try to calculate what is probability. And again, so Q is uniform. So all the entries here, Qij here are uniform over FP. So the makes life easy. So let's just, so this is the part that also Mark mentioned in his lectures, is that we do for our IAD matrices. So the columns of the matrices are independent. X1 is the first column, and then so on. So we do the column exposure process. For each m, so m starting from 1 up to n, right? And then we look at adding a new column, would it increase the rank or not? Right? So the rank is always increases or increasing. Right, so we see that, so Wm is the column space generated by the first m columns, and then we review the next column and we're asking whether it belongs to that subspace or not. If it belongs to the subspace, then the rank stays, right? Or the dimension, the rank is the dimension here. And if not, then the rank is increased by 1. What is that probability? The probability is quite easy. So assuming that Wm has dimension L, or rank L, then the probability that the next column belongs to Wm, right? The probability with respect to this is just the size of this subspace, which is P to the L, over the size of the whole thing is P to the N, which is, we get this number, 1 over P to the N minus L. So this exactly because of the uniform. So just in short, the rank of the next subspace is the same with this probability, and it is increased by 1 with 1 minus that probability in that case. So putting everything together, we can calculate what is the probability, the rank of the final matrix is n minus d by adding all those possibilities. So namely, having co-rank d means that in this column exposure process, there are d times that Wxm plus 1 belongs to the subspace generated by the previously exposed columns. We sum over that and we get this kind of like rather ugly formula, but it is exact formula. We could get a nicer formula if we send n to infinity, then because n is infinity, so some of these quantities is 1. So we get a little bit nicer quantity, namely involving 1 over d to the square and all this kind of thing. It's kind of interesting to me is that the limit probability here, of course, it makes sense, but it's not easy to see. It also forms a probability distributions over the non-negative numbers, and it follows from Euler's identity. It's kind of nice things that the limiting object is also a probability. And for all other aspects of the studies of this talk, the limiting is always a probability distributions by some algebraic reasoning. Yeah. So in your yeah. Product from this one. There are many things. I from to n, and in here is I from 1 to d. Yeah, if n is infinity, then that becomes this. You cancel it out and you get this. Okay, so this is for ID matrices. For rectangular matrices, you have similar things, by the same reasoning because the columns are independent. Okay, so that's all for ID matrices. It's kind of I don't know, that's a good thing. So now for symmetric matrices, again, so I denote it by M. There's M, I don't know. So all the entries here are uniform up to symmetry, are uniform over AP. And again, we're interested on this basic statistics, like what is the rank of this? So would it be similar to the IAD matrices? And we expect it's not, but how different? Okay, so we're interested in the rank. And again, so now we see that the column exposure process doesn't work because of the dependencies of the entries. Right? When we reveal, we cannot do it. But this also mentioned in Mark's yesterday's lecture is in symmetric, we kind of doing kind of corner exposure process instead of doing the column exposure process. So MM be the minor generated by the first M rows and the first M columns. And then I'm going to expose the next column in the dimension M plus 1, right? And to see how is the rank evolved. Right? So assuming that this matrix has rank L, some L smaller than M, at most M, and then we'll see how is the rank of the next minor evolves. We see how to do it. So let's see, assume that this one has rank L, then I'm exposing this whole row, but let me just forget about this. I'm looking at this M-dimensional. And if this M-dimensional vector doesn't belong to the subspace generated by the rows of this, then when I expose this next rows, it will be, the rank will be increased by 1. And at the same time, the rank here also increased by 1. So the rank will be increased by 2. So that's what I summarize here. So assume that the rank is L, and assuming that the first L rows of this generate the subspace, and so the rank is not increased by 2 if and only if this vector belongs to those subspace of WM. In other words, and then this property we already know because this is independent of WM because of the independence, right? So we know that this probability is 1 over P to the n minus L from the previous calculation. All right, but now we have to decide. So this is the rank is not, the rank doesn't increase by 2, means that it is either by 0 or by 1. Then we have to distinguish 2 cases. So let's see. So let's see. The rank stays. The rank stays means that right. So not only that this belongs to the row space of this, but when we expose one last entry here, the extended row here also belongs to the extended rows here. But if you can, then you get one more equations, namely you have an equation that xm plus 1 equal to some linear combinations of the entries here. And the coefficients there is determined by how is this rows depending on the previous one. Okay, so that is the equations that we have here, that beside these conditions, we also have these conditions. And then here the randomness, we condition on this, the randomness on this. Okay, so putting together, we see that the rank doesn't increase at all. It has two conditions. First is you have this, and second is you have this equations. So that makes its probability is 1 over p minus L and 1 times 1 over p because of the second equation. So you put in together, assuming that the rank is L, then when we expose the nest minors, the ranks doesn't change. That happens with exactly this probability, 1 over p minus L plus 1. So the rank is increased by 1, will be this minus that, and the rank equals to 2, increased by 2 will be 1 minus the whole thing. So we have 3 possibilities with given probabilities. And then we're putting together, so we know the transition probability, so putting together so we can get this formula for exact formula for the, so this is exact formula, there's no limit. So exact formula when the co-rank of the symmetric matrices is D, which is essentially different from the IAD. And it makes sense, right? Okay, and taking the limit, we have this nice formula that the co-rank when n to infinity is this number. So it's a number, if p is fixed, then this is a number. It doesn't go to 0. It's for p is 2, 3, and so on. And this limiting is also forming a probability distributions by another Euler's identity. I find it amusing. Okay, and so this rank statistic of symmetric matrix is also studied well in the past by Collins and by Mac Williams, and from a different context. Okay, so we have covered IAD matrices, symmetric matrices. So the next one is similar to symmetric, but alternating. So skew symmetric. So skew symmetric is the ones that are 0 on the diagonals. Right? And then you have anti-symmetric of the entries, which is back to the main diagonal. Right, so as guided by the symmetry case, here we study again by doing the Corner exposure process by revealing this principal minor, and then we consider the nest columns and rows. Right, so so again, the rank increased by at most 1 by the same reasoning as we had the previous situation is in this row belongs to the row space of this minor, and that probability is we can calculate exactly. Right, but there's some funny thing happening here is that if the rank doesn't increase by at most by 2, then it will be the same. So there's no situation that the rank is increased by 1. So it jumps. So it's from 0 to 2. So there's no 1 here. And this is because of some linear algebra reason is because of the bilinear form of alternative matrix is always 0. Quadratic forms, it's always 0. And so so just grab it here, just summarize it here is that, okay, so the rank is either stays with this probability or the rank increased by 2 with the complement. So when that's how the rank evolves in skew symmetric matrices by that algebraic. Okay, so putting together, so the co-rank, right, is always has the same parity with n, or the rank is always an even number. The rank of skew symmetric matrix is always an even number. So we get this complicated formula, and then when we set it to infinity, we get something funny distributions. Is that all right? For any fixed d, then we have to take n as the same parity of d to see the limit. So if n has different limit parity, then you get 0. So There's no limit, actually. So you have to look at the N as the same probability. So there are two ways to summarize that, or you summarize this way. So you send N to infinity, put N is even or N to odd, and then you get two different distributions of the rank for skew symmetric matrices. All right, so far we have covered IID, symmetric, and skew symmetric, and I ran out of models to do. So the next step is I'm going to do product of matrices. So to see, I'm just out of curiosity, I was wondering if we take two uniform matrices, ID matrices, uniform matrices, and multiply them, would they stay uniform? It turns out it's not. Right? If you look at the rank of it, so the product has less chance to be invertible compared to each of them. So it's not. Right? Then the question is, what would be the rank, even for the uniform model? And I got stuck. Like, for example, look at the two matrices, Q1, Q2. When it has full rank, then each of them must have full rank. That's easy. But when they have rank n-1, then what would be the possibilities? So one of them must have rank n-1, or both of them could have rank n-1. And the image of this must not belong to the kernel of the other, and so on. So there are situations, there are difficult situations. This is hard to do. And let alone to have to calculate rank n-2 and so on. All right, so how do we do that? And being a little bit more ambitious, we are interested in the joint studies of the ranks. Like you have K matrices, then we're interested in the ranks of Q1, Q2, Q1, Q2, 3, and so on. Definitely the rank of this is at most of that, so you have a decrease in sequence. And for now, K is fixed. It turns out that I was looking at the wrong way. So there's an easy way to calculate using the invariance of the uniform. So let's just look at the case 1, case 2. You have two matrices uniform, Q1, Q2, IID, right? I didn't say. And let's try to calculate this probability that the first matrix has rank n-R1, and the second matrix has rank n-R1, R2, R1, R2, and non-negative integers. Okay. So the first, let's just try to condition on Q1 has rank n-R1. Then I can use the Smith-Normal form to bring it back to the diagonal form. Right? Diagonal form is the matrix I n-R1, where the first n-R1 entries are ones, and the remaining R-1 entries on the diagonal are zeros. And so I can use two non-irreducible matrices U and V to bring it back to this diagonal form. And condition on this has rank n-R1. Then the law of Q1, Q2 with respect to Q2. So because Q2 has the same law as VQ2, because Q2 is uniform, this uniform is invariant by multiplying by non-invertible matrices. So these two probabilities are the same. But this new matrices has a very nice form that it says diagonal times Q2, the identity, a partial identity of Q2. So basically, with respect to Q2, the probability with respect to Q2, that this matrix has rank n-R1, R2, right? And Q2 is independent from Q1. So this turning out to be the probability that we have considered before. So it going back to that the probability you have a rectangular matrix of this size n-R1 by n has this rank n-R1 R2, which is exactly the rectangular cases that we considered before. And then we know what the formula that is. Okay, so gathering together. So because the formulas are a little bit cumbersome, so I'm using the Bockhammer notations. And then with that notations, we can summarize what we have done. Is that this probability is this formula. So there's an explicit formula for that. So that's when this is the joint rank statistic of two, the matrix Q1 and Q1, Q2. And we take it to the infinity, you get this nicer formula. And by the same reasoning, we can do the same for joint statistics of K matrices by the same reasoning. Conditional Q1, conditional Q2, and so on. All right, so we have that. These are the focus. Okay. Right, so the rank statistics of products is different, and we cannot use the classical rows or columns exposure process, but we have to use invariants. Okay, so one of the first main result of this that we did is that all of these statistics are universal in the sense that instead of uniform, you can replace it by any non-deterministic distribution. So any, you can do 0, 1, you can do weighted 0, 1s, and all such, as long as it is random. So this becomes is universal. So, okay, so for the case of IID cases, people studied in the 90s by combinatorialists, by Charlotte, Rees, Rubin, Plummer, Karp, Guerzo, Cooper, where they fix P, right? And myself and Elliot and Lou, Mihan, myself, and Wood. So in the symmetry cases, it's studied by Ferber, Chen, Sarsone, myself, and Wood, and the symmetric, anti-symmetric cases, and by the product matrices cases by myself and Van Persky. So there are a few comments. So there are situations that we can send P to infinity to with N, which it's a little bit harder to do. So these people, they just fix P, but for example, these papers, we allow P to grow to N with some exponential. So we can allow P to go very fast in that, and then we still get universality. For these works, we have to assume P to be sub-exponential in N. We can do that. So sub-exponential. For this, we can do a sub-exponential. For this, we just do fixed P, basically. For P grows, very slow to N. So we cannot do a fast grow in here, in this case, because of the method. But it is important to send P to infinity because of some other things I want to be discussed. Okay, so these are the basic rank statistics, and I'm happy to see new distributions and such. So the next statistics I'm going to talk about is a little bit involved, more involved. So the so-called co-kernel statistics of matrices. And we can read the rank statistics from the co-kernel statistics. So everything that I did so far, we just forget and then just look at the co-kernel statistics, and then if we see it, we can read the ranks from it. Okay, so here's the situations. So you have a ring, a commutative ring, and the entries, let's say square matrices, right? Where the entries from the ring are, and then you quotient out the images of the matrix by the space R to the N. That gives you a group. It's a abelian group. So there are typical examples that we'll be focusing on. The netro is when is in Z, or Z mod MZ, mod M, or the periodic integers. So the question is statistical. So assuming that P is random, Q is random, sorry, what would be this object? How does it look like? This group. All right, so I think the easiest way to visualize is when R is Z, right? So it's integers. We have a matrix of integer entries, somehow random. And then, so this is a sublattice of Z to the N. You quotient out the sublattice, you get an abelian group, right? And what it would be, that statistics. So it's, but methodology, it is easier to work with. So all the statistics can be computed by using the statistics over periodic integers. So I'm going to focus on that now. It looks a little bit harder, but this is where all the intuition comes from. Okay, So let's just recall a little bit about the Yeah, so this is the lattice Dn, and this is the sublattice is the matrix of Q, right? And then you quotient out, you get a. I don't know. For example, the determinant, the size of this group will be the volume of the fundamental domain, for instance. Those are known. Yeah. Okay, so for the periodic numbers, so everything can be written as a power series of P, right? Or the entries, the coefficients are numbers from 0 to P minus 1, except the first entries is where the entries are non-zero. So its coefficients here is from 1 to P minus 1. So K0 is called the order of A, and K0 sometimes can be negative too. So we define the absolute value, the periodic absolute value of A is just P to the minus K0. And the periodic integers are those where K0 is at least 0, where the absolute value is at most 1. So this group is locally compact and topological group, so it has a Hall measure on that. So we modify so that the measure over the periodic integers is 1. Okay. All right, so the setting is we have this n by n matrix where the entries are Hall distributed over ZP, okay, over the periodic integers. And we consider the co-kernel. So the co-kernel is again R to the n, Q, R to the n. So now it has specific forms. It is a P groups. So the order of that will be power of a P. And so abelian P groups can be factored out related in these forms, right? As product of cyclic groups. So every group here can be identified with a partition. There's this increasing sequence. So we can identify a P group with a partition. So because the partitions, it involve a little bit of things, so let me introduce a bit MI. That partition is the number of parts of size I and the conjugate of the partitions. It is relevant because all the statistics has some the size of the automorphism groups of P, right? And if P is the matrix is a group of this form, then the size of the automorphism groups can be as an exact formula like this. Using the conjugate and the Pochhammer symbols. Okay, so the first result in the literature regarding this model is by Friedman and Washington in the 80s, where they calculated that if it is uniform, Hall distributed over ZP, then the co-kernel, the probability that the co-kernel is isomorphic to a given P group is inversely proportional to the size of the automorphism that group, and there are correcting factors here. Okay, yeah. All right, indeed, they are able to show a more explicit formula where if you send n to infinity, you get back to this formula, just like we calculated the rank. So they, and then here it also involves certain rank of the matrix that. All right. And just one comment is that this limited distribution is also turns out to be a probability distribution over P groups. That namely the sum is 1 over all P groups, and it follows from fascinating facts follows from Cauchy identity. If I have time, I can mention it. Okay, so I don't know if it makes sense or not, but I will try to convince you why they got this formula. It's a little bit difficult because, if we cannot explain for the nicest model, then there's no way that we can understand what this. All right, so let me just summarize a bit how the proof sketch of that is that So let H be a submodule, ZP submodule of this, let the ZP to the N, where the quotient is morphic to the group B that we would like to consider. Then there's a formula by Cohen-Lenstra saying that the number of such submodules is exactly this number, and that is where the automorphism, the size of the automorphism group pops out. Now it is taking this for granted, then I let Q0 to be any matrix where the column space span H. Okay? Then this is the formula that I told you before. This that the determinant of the matrix is the size of the group, but here we do the absolute value of P, so it's kind of reverse. So it will be 1 over the size of the group. And so it turns out that if you have Q0 is 1 where the column space is H, then you look at all matrices that form Q0A, where A is invertible over ZP, then the column space of this matrix is also spans H. So the probability with reverse to our matrix where the column space is H is, so I'll remember, so mu is the product measure over the whole unitary entry-wise. So the probability that our matrix belongs to this set, this Q0A. So, and so now you can calculate, so the probability of this matrix, the measure of this set is the determinant to the N times the measure of GOM. The determinant to the N is because you just imagine assuming that this matrix is diagonal, then you multiply a diagonal matrix by, you look at the determinant of the new matrices, everything will be raised to the power of N. So there's the power of N here. So what left is just to calculate what is the measure of an invertible matrix over ZP, and that is exactly the formula that we seen before, is that it is essentially the same, that the probability that over FP, the matrix is non-singular, and this is the factor that gives you that number. And then now the remaining is we need to sum over OH, where the quotient is B, and you sum over OH, this will be cancelled out. That leads to this, and then you have 1 over the size of the automorphism. So that's the sketch of the proof of the uniform model. Any question? Okay, so my next slide is on something even harder, but related to what we discussed before, is for symmetric models. So the symmetric models, again, uniform, how distributed, sorry, with respect to symmetry, then people can calculate that the property that the co-kernel is isomorphic is the correcting factor is a little bit different, and here you have again the size of the automorphism group and also the size of P. And there's a reason why the status is different, is because I mean I just keep this, but because there are symmetric matrices, it comes with a pairing entries. So it comes, it will induce a pairing over the group as well. So it's called symmetric pairing. And so the co-kernels comes with the parents, and then you have to sum over all the parents and all such. So that gives you a different formulas like this. But basically, people were able to calculate this way. So that's for symmetric matrices. And the situations for skew symmetric matrices is also weird. That you have to look at, again, for how distributed entries up to symmetry, then you have to look at the group that is square periodic groups. So it's the regular groups, the statistic will be 0, but so SP here is the square of P groups. So it says the form H cross H. H is P group. And this, we don't see the automorphism group anymore, but we have to look at like the automorphism groups, which is preserves certain alternating pairings. So the alternating pairings is come together with this matrix. So the statistics is different. It's getting more involved a little bit. Now for product of matrices, then the formulas is different in a different way that involves Hollywood polynomials. So if I have time, I can introduce a bit, but for now, let's just take for granted that, so Van Persie calculated very recent results that for IID distributed entries, the joint co-kernels statistics of these partial products can be written as using the scale dual Hollywood polynomials. And T here is 1/p. So I will introduce later if I have time about this. But actually, it's explicit, so you can calculate. You have using a little bit of algebraic combinatorics. And so if you want to calculate only the co-kernel of the final product, then basically we have to sum over all, this is the marginal, so you have to sum over all the realizations of B1 up to Bk minus 1 and from this formula. So basically you can calculate the co-kernel of this, right? So as I said, the way we got the rank statistics before is we come from this formula, so co-kernel statistics, and we read the rank statistics from the co-kernel, the way we did. So that's that. So parallel statistics of all the matrix models that I have mentioned. All right, so the message is that all of these statistics are universal in the following sense. So first, if we work over ZP, then we don't have to assume how distributed. We can assume either it takes value 0 or 1. And the other, in the other sense is we can also look at the integer entries, right? And we look at the co-kernel. So the co-kernel of that will be a abelian group, and then you look at the P0 subgroup of that. So that also gives you the statistics as we have seen for ZP. So, okay, so the IID case was proved by Wood maybe 10 years ago. Symmetric cases are new, especially if we carry what the growth of P. Scale symmetries and for matrices in recent joint work with. So that will be all I would like to talk about. But maybe I will discuss some proof method, and then amazingly, it has something to do with what maybe Mark discussed in his lecture. But let me just try to spend real quick. This slide, so all the motivations coming from basically statistics on algebraic number theory, I will skip, but people basically use this to predict certain distributions of class groups of certain quadratic field extensions of the rationals, and then elliptic curves and also symmetric skip. But it's the motivations of the universalities we want to show that the models is robust. Okay, so let me just try to introduce something nice. How do we show certain things are universal? So we use the so-called moments method. I don't know, it makes sense to call moment method, but basically we just, so Y is a random group, P group, so G is a P group. So we try to calculate the number of surjective homomorphism from Y to G. Okay, and the expected value, the expected number of surjective homomorphism, which is denoted by Mg, so G. So why would people call it moments? It has something to do with if you look at, so there's a relations between surjective homomorphism and homomorphism, namely there's a close connections. But if you look at the homomorphism of the group to this Z mod PKZ, this cyclic group, then you will see that you get the K moment of the co-rank statistics. So it has something relations to the moment, actually the kite moment of the usual the kite moment in our probability. All right, so but the main thing about all of this is that we are able to calculate the aspect number of suggestions, right? And it is asymptotically 1 for the IID model. So the moment is 1 for every G, every fixed G. The moment is 1, which is fascinating. And so you see that the model is either uniform or not. The moments are asymptotically the same. So then we have to develop kind of like comparison, like moments from distribution from moments. But we mentioned that later. But let me just try to explain why we get this these identities, which is the main thing in the approach that in our universality. Okay, so let's just try to convince that you guys that. All right. So just so again, coming from the first few slides, so x1 up to xn are the columns of our matrix Q, and v1 up to vn are the bases of our space or n. So every matrix can be viewed as a homomorphism from V to V, and the entries, the columns, the J columns is just M of Vj, can be written in the basis as these entries. So these entries are supposed to be random, and the co-kernel is just be quotients of MV. All right, so we'll just try to, so every suggestions from this co-kernel to this group G is fixed, okay, leads to a suggestions to the space, to V, G. Because these are quotients, so you lift up to V, so you get a suggestions from V to G. Then the number of suggestions will be just the sum over all the suggestions from V to G, okay? So now from V to G, there's nothing to do with M anymore. But where F sends the image of this to 0, and then you have to calculate this probability. So basically, here you look at all the suggestions from V to G, and then here you look at this probability. And that probability, amusingly, can be written as because of independence of so this is from J to N, sorry, N. The probability of the image of each columns is 0. When we can write that F of X, so F is a suggestions from V to G. Each suggestion is a surjective homomorphism, so it is uniquely determined when you look at the images over the basis. So this, and the image of the basis must, because it's suggestions, so it must generate the group. So you look at that kind of n-dimensional vectors where the entries are from G and they generate G. So these entries generate G. And you can imagine, you can write F of X as a linear form in the combinations of F1, X1, Fn, Xn, where X are the kind of the entries of this column vector, and then you have a linear form. Right. So basically, we put together, it's just basically related to Mark's lectures, is basically we are trying to calculate what is this probability, a probability of a linear form where the Fi here, F1 up to Fn are fixed, the X1 up to Xn are random, let's just say random over G, and then we want to estimate what is this probability equals to 0, right? And then we have kind of, because of linear, so we have kind of that probability raised to the power of n. And then we sum it over all, we have to sum over all the suggestions, the possible vectors here. So basically, intuitively, for the uniform model, so this is a random sums in the groups, right? So it is it's comparable to the uniform measure over the uniform distribution over the group. So the probability is equal to 0 is 1 over G. This automatically follows from the uniform model. Now for the non-uniform, let's just assume that this guy's take value 0, 1. So you have a sum of 0, 1s, F1, 0. So these are Bernoulli, 0, 1, right? And then we are trying to estimate what is D-probability equal to 0. So it turns out that we can show that for the most choices of the deterministic factors, F1 up to Fn, this probability is comparable, is 1 over G with a very exponentially small errors. I said that we have to classify. So there are bad examples. For example, auto F1 up to Fn generate a group, but most of them belongs to a subgroup of that, except the last one, the first one. Then the probability here is not comparable to 1 over G. So you have to classify the Fs where you don't have that situation. So I call it genuine. Genuine suggestions means that not only the F1 up to Fn generate your group, but you drop a positive portion of that. The remaining is to generate a group. So it might be in connections to the complex matrix or real value matrices. This belongs to like non-sparse normal vectors that you get probability equals to 0 comparable 1 over root n. All right, so that's the whole thing. The whole thing of the business is try to study certain random sums, how to compare it with the uniform, with the measure over the group, and we have to classify the suggestions. We have to show that the number, the distributions coming from the bad suggestions are small, negligible. So if we just take 1 over G for granted, then we just see that this probability we get it is like 1 over G and to the n, and the number of suggestions is basically G to the n. So we have to show that, but these enumeration things, we have to show that the number of genuine suggestions is order G to the n. So G to the n divided by G to the n is cancelled out, so you get 1. So that's how we got 1 from all of this thing. Okay. So now, so we are done with the proof of basically the proof of of this theorem that the number of suggestions in expectation is 1 for every fixed G. And so the remaining we just calculate, we just use moment comparison things. Is that so you have two sequences of random groups that have given the same moments, then the distributions are simply the same. So this moment comparison thing, right? And so now we look at the uniform model, we see that the moments are exactly 1. Now for the non-uniform models, we see that the moments is asymptotic 1, so they are comparable. And so the distribution must be the same, and the distribution from this, we already see it before. So that's why the distribution of the non-uniform model must be asymptotically the same. Right, so and then people, so Nguyen and Wood recently, they developed this kind of machinery to a higher, much higher level that basically from a moment itself, you can read the distributions by doing kind of the Mobius inverse theorem. And then they also show robustness and so on, and the very general development in that. Okay, so basically I'm done with my talk, but just a few remarks that and then. So all the metrics, I'm always looking for all the natural matrix models, and one thing comes up is I don't know, maybe polynomials of matrices. So we look at the product. But for example, we still don't understand, you have an IID matrix A, Q, and then what is the rank status of Q square? We don't know. But maybe there's some reason that the simple reason that we missed, but we don't know. And what is the co-corner status of that? I don't know. And of course, I mean, for more general polynomials, and also you have a few polynomials, you study the Ghosh statistics, perhaps. So this kind of, so and another amusing fact is all of the models that we have looked so far, the moments are so nice. For example, when for square matrices, the moments is 1, For rectangular matrices, the moments even smaller, 1 over size of the group to the U. For the matrix products, amusingly, the moments is the number of chain of subgroups of the K chains of your subgroups. It's amazing. We found out like the number of this is the moments of the matrix models, which is amazing. Another thing is people are interested in, and we find it natural, is we look at the global statistics, is that we are not looking at, so assuming that the matrices are integers, the entries are integers, and then we look at the co-kernel of this, so we know this is z to the n slash mz to the n, so it's a abelian group, and then we are just looking at the genuine distribution of this compared to what we did before is just we look at the P0 subgroup of it. So we call it, this is global statistics, and this is like local statistics, I don't know. We just look at the coordinates of the random vector. Yeah, so we study this model, this universal statistics, global statistics a little bit for various models, including other models, the IID, symmetric alternating, and also kind of like Laplacians of random graphs. And it is a little bit technical, but this model will submit to be very dense. So I just showed you, but the parameter P is very dense, so we don't know what happens when P is smaller. So with this, I would like to conclude the talk, and thank you so much.
Thank you, Hui. So any questions? Any questions? If not, maybe I can chip in with a couple of questions of my own. So what? These kind of matrices with entries from a finite field. So are they of interest due to some connections to other fields or some applications?
Yes, I have to read details, but so people in computer science, they look at the rank. That is basically just the rank.
And why is that interesting?
I don't know. It's from error correcting code or something like that. But
I'm sorry?
Error correcting code.
Error correcting code. Okay. And the other question is, so you mentioned that this homomorphism count is a proxy or is an analog of moments.
Right.
In this word.
Yeah.
So can you motivate to us why that is the case? Why should we think of these objects as?
Yes, I think, yeah, that's a good question. So, so for example, you look at the homomorphism of, right. So if you look at the homomorphism of your group, P group to this cyclic group, it reads you the co-rank of the matrix, the co-rank over P. So the expected number of homomorphism from that to that is E, this is the kth moment of basically of the co-rank. Okay, so R is like, this is the co-rank, so the P powers of the co-rank. What you see like this is really the basically functions of the co-ranks to the power of K. Yeah. And from the Hom and the sum, they are kind of dual to each other, so it's easy to read from the homosexual for homomorphism. But
so in some limit, let's say, suppose P going to infinity, and maybe I take some kind of scaling limit, so they do these objects reduce to usual moments?
No, I don't think so. Yeah.
Finally,
let me just try to complete this. So I think people in number theory, so they were interested in the class groups, right, of quantity extension fields, and then people look at the rank statistics of that group over P is 3 or so on. And then, so I think Fury and others, they calculate, and they were able to show that the statistics is correct, is that common. So basically, we were interested in the distributions, but actually it makes more sense to study the moments of them.
Is it correct that there is a theorem which basically an invertibility theorem which tells you that if all these moments are specified for all k,
exactly,
then that determines the distribution?
that's right. That's a very good question, and I think Nguyen and Wood they follow that approach. So you can read. They give you if and only if conditions which numbers could be a moment. And from the moment,
think of moments, can we think of something like Fourier transform or character?
Right, that's so they don't do Fourier transform, but they do inverse Mobius functions because things are discrete here. But they use kind of so you can write this, the suggestions as a functions of distribution, and from there you read the distribution directly from the moment by the Mobius inverse transform.
And other than explicit expressions for probabilities of various events, so is it possible to think of other usual probabilistic objects in this world? So for example, if I try to think of some kind of a CLT, let's say we consider the situation where P is growing much faster with respect to N, then is it possible to?
Yeah, we don't see any CLT, but there are two things. For example, one interesting question is to see, we have all the limits distributions, but how is it depend to N? For instance, like what is the speed of convergence? That's one thing. The other thing is, for example, as you said, this Van Persky, he considered a co-kernel a product of matrices, and he looked at the distributions of, so the distribution of the largest part in the partitions. He established like what is the evolutions of that when K goes to infinity. K is the number of matrix products. So he studies like he got some CLT fluctuations of that.
So any other questions? If there are no questions, then let's thank Hoi once again for the talk. And this brings us to the close of the first session.